Hi, so I'm going to show you how we can go about doing this part of the assignment. It says here quadrilateral ABCD is a parallelogram. And it says here to sketch this parallelogram, and I'll draw it. Both pair of opposite sides are parallel. So I have here ABCD, and I'm going to label this in clockwise order. You'd never want to zigzag. You can go clockwise or counterclockwise. In a parallelogram, both pair of opposite sides are parallel. So I'm going to mark these sides as parallel. And it says to draw a auxiliary line to break this into two triangles. So my auxiliary line is a line that extends from point B to point D. And now I have two triangles, and if I can prove these are congruent, then I can show that the opposite sides of a parallelogram are congruent. That is my goal. So to do this, I'm going to start by saying what is given. Let's see. We know that angle CBD, which we'll call angle 1, is congruent to angle ADB, which we'll call angle 2. Angle 1 is congruent to angle 2. Why? Because they're alternate interior angles formed by a transversal crossing BC, parallel lines BC, which is parallel to AD. Since it crosses parallel lines, the alternate interior angles are congruent. The second thing I'm going to point out is that BD is congruent to itself. So BD is congruent to segment BD. And we would call this is because it's a common side. And I could say DB instead of BD. BD is congruent to DB. It's the same side. We could say it's a common side. Or we could say the reflexive property. This is a little bit more formal way of saying it. Third, we know that this angle is congruent, which we'll call angle 3, is congruent to this angle, angle 4, because the transversal crosses these parallel lines. So angle 3 is congruent to angle 4. Why? Because they're alternate interior angles formed by a transversal crossing parallel lines AB and CD. Now, at this point, I'm going to point out to you that we have, in the one triangle, we have one angle, which corresponds to one angle. This is the angle. We have a side from the one triangle that corresponds to a side in the second triangle. And here we have the third angle, which corresponds to a third angle. A third part, which is the second angle. So we have angle, side, angle. So at this point, I can go into my proof, and I can say, well, triangle, let's see, this is 2 ticks, 1 tick, no ticks. So I could say triangle DBC is congruent to triangle, let's see, 2 ticks, 1 tick, no tick. That's BDA. And what's my reason for that? Well, it's the angle, side, angle triangle congruence theorem, the one that we proved before. Since we've proved it before, we can use this in another proof. I don't have to go show you what transformations take this onto this one. I can just say it's because I know that if two triangles have two angles congruent and their included side, then the two triangles are congruent by the angle, side, angle theorem. But this is not what we wanted to prove. What we wanted to show was, let me make this a little bit larger, that the opposite sides are congruent, that this side is congruent to this one, and this side is congruent to this one. And I can do that in one step. I'll do that here. I'm going to say segment AB is congruent to segment, AB is congruent to segment CD. My first and last letter, last and first letter, I guess. And we can also say that segment BC, which is my last two letters here, is congruent to segment DA. That's BC and DA. Why? What rule can I give for that? Well, I used a shortcut here to show that the two triangles are congruent. Once I know that the triangles are congruent, I know that all of the corresponding parts of the congruent triangles are congruent. So this is how we use CP-CTC. We show that the two triangles are congruent first by one of the shortcuts. And then, since they are congruent, all of their corresponding parts are congruent. This means that the opposite sides of a parallelogram are congruent. We can now use this in a theorem because this is a theorem. We've proved it.